coherent. And then, of course, we have particle magnons. Unfortunately, is some not very long time living particles, so they decay. And due to the decay, the amplitude of signal changes and frequency also changes due to the interaction between magnons. But we can make some kind of the measurements of amplitude and frequency and the phase of the signal in some instant time. And here is shown this histogram where we have tried to measure simultaneously the frequency of the signal and phase of the signal. And what you have seen uncertainty. If you want to know exactly the phase, we don't know frequency, and vice versa. So this is very fundamental principle of quantum mechanics. Uncertainty principle is working for Bose-condensed magnon state. So the first helium-3 magnon Bose-condensed state was found in in 84 in Moscow, in Institute Kapitsa Institute. Then in Kazan we have found the same state in magnets, in antiferromagnets. And that time we have excited by these conditions because now it was something 1,000 times higher temperature. It's 1 Kelvin temperature. And with Murat Tagirov, we have suggest that we have Bose-condensed state. That time there was very discussable discussion about possibility of quantum computing, and we suggest to make quantum computing system on this system of Bose-condensed state of magnons. Later, the Bose-condensed state was found also in yttrium-filled garnet, but at room temperature. So what is very important things is that if it's possible to make quantum computing at room temperature and not cool down to extremely low temperatures, that it can be very important achievement of civilization. So now we are working about possibility to do quantum computing on the magnon Bose-condensed state, and furthermore, just we are sure that it's possible to do it at room temperature in principle, but of course there is many problems with relaxation. So coherent time is relatively small at room temperature. So we need to go down to lower temperatures to demonstrate quantum computing and then return back to high temperatures, to room temperature for the applications, future applications. But there is not only Bose-condensed state, there is also the magnon superfluidity. And now I just want to show you very recent results. We have the yttrium-filled garnet film with the shape of ellipse and strip line, which excite magnons just in the region of strip lines. And here is the amplitude, the magnetic field. This point is resonance frequency. So we sweep the magnetic field with very small power excitation, and we have seen that we have excite magnons, and then it's some kind of slightly deviated Lorentzian excitation line. Here is the phase portrait, phase of this signal. Signal we have measured by optical method, and we can sweep optical sensor along the axis of ellipse. So here we have seen the excitation of magnons locally, and there is no excitation in the other part of the sample. If we have seen the phase of this precession of magnons, then we have seen here just spin waves, which excited in the region of excitation and then move out. Now we have increased the power, we increase the amplitude of magnetic deflection, and let's see on the last picture, we have a very big signal. What is important? Here is not spin waves. Here is the coherent precession of magnons, just far away from the region of excitation. So this is very new result, which shows that we have real transition from the spin waves mode to the Bose-condensed state. You can see the phase here is just homogeneous. Now, we have suggested with Murat Salikhovich in 2019 2011 to use this Bose-condensed state for the computing, quantum computing. We have invited Andrianov and Moiseev in office in Kazan and suggest them to try to make a theory on this basis of this application, this phenomena for quantum computing. And they have made the article, which was published in 2012, which has the first proposition of this method. But unfortunately, there was not really anything important, only some suggestions. So this article doesn't deviate much from suggestion itself. So what is important for quantum, for Bose condensation state from point of view of quantum computing? First of all, because quantum information is not subject of only one particle, but it's the subject of huge number of particles which are in covariant quantum state. These particles duplicate the quantum information, so make this information much more stable than the case of this just single quantum particle. And what is very important also, that if you have create new particles, added new particles to the Bose-condensed state, that this new particle, according to Feynman theory, just created exactly the same conditions. So it means that we can keep Bose-condensed state with given state permanently, how it was just shown in previous slide. So we have pumped permanently magnons, and then magnons moved out, of course, decay, but the state remains exactly the same state. So now let's go to the Bose-condensed quantum computing. First of all, there is many suggestions to make atomic back qubit for computing. And this is just one of the picture, one of the suggestion. When they supposed to make a special trap for atomic back, separated by space in two parts. And of course, between these two parts is entanglement. So this very important phenomenon when one particle knows the phase state of other particles. And here you can see the possibilities to make some manipulation of these states by different additional excitations or by interaction between these two clouds of atoms. And this is prototype for quantum qubit based on the atomic Bose-condensed state. We can go exactly the same way for our case. For example, one of the suggestions for magnonic qubit was the next one. We have one yttrium-free Garnot sample and other yttrium-free Garnot sample put in the resonator. Of course, each yttrium-free Garnot state, magnons excite photons. And these photons can go to the other sample and absorb it. So this means that we have entanglement between these two samples. Furthermore, we can excite these two states by external microwave pumping, and also we can measure the existing state by just leakage of the photons, radio frequency photons or signal. This suggestion was made for the point of view of just single magnons or small number of magnons. We have tried to apply this idea to the the Bose-condensed state. For this, we have made a resonator in frame of the in shape of the frame, and put 3 samples of yttrium Carnot state in gradient of magnetic field, just for separate the 3 samples. And in the small excitation, we have seen 3 main lines of magnetic resonance. What happens if we have increased the power? This is the increase the power. So it's small power. We have seen just signals here, here, and here. If we have increased the power, we can shift the frequency of the signal when we have changed the magnetic field. So the signal follows to the magnetic field, and the amplitude increase, because this change of resonance means that the change of angle of deflection of magnetization, and means the increase of number of magnons. So finally, we have seen a signal when there is a many magnons, and this many magnons correspond to the conditions of Bose condensation. So we have increased more and more power. We have seen more and more longer this non-linear magnetic resonance. But now let's see. If small power, we have somehow its state destroyed. For example, here, start from the second sample and destroyed here, third one and destroyed here. Increase in power. Then the state go up more. And here, for example, in this region, we have simultaneously excited magnons from one sample and other sample. So there is now exciting of 2 samples. And even further, there we have seen the exciting of 3 magnons of 3 samples. What does it mean? It means that we have prepared the superposition of 3 coherent quantum states here. So how we can use it for quantum computing? This is initial state. Now, if we have switch off the magnetic excitation, then all these 3 samples should decay separately. What does it mean? It means that the number of magnons here change with one velocity, here with other, and then with third one velocity. But they are interact each other. So we have entanglement, and it means that we have interaction between 2 samples or 2 Bose-condensed state. Now we have possibility to make some kind of separately do something with one of this quantum state. For example, suddenly we have changed the magnetic field locally. Then we have changed the state of one qubit of one state and not change the other state. There should be some kind of the quantum phenomena of quantum exchange between these 2 quantum states. And this possibility to this quantum computing now is under discussion. One of the possibilities, one of the prototype. Just, you see, my talk is prototypes, not just suggestion of prototypes, not show the result, unfortunately, yet. Other possibility. You see, we have always yttrium Carnot in the optical, in the cavity, radio frequency cavity. It's well known that if we have a mode of photon, radio frequency photon in the resonator, and Kittel mode of precession of magnetization, they are split. There was suggestion and shown experimentally that this 2 state can be considered as a 2 state of qubit, 2 quantum state of qubit, and it was experimentally even shown by switch off phase between 2 states. We have seen coherent precession or oscillations between these 2 states, and again coherent by some additional pulses. How it can be, it's again was shown for the small number of magnons. How it should be when we have a Bose condensed state. Here are experimental results. You see, now we have tried to see the signal from the disk, which was excited by strip line on the side of the disk. In this case, we have excited the coherent precession main line, or we also can say the of the edge state precession, which is mainly excited on the edge of the sample. And frequency of these two modes are different. So if we have made a relatively small power, and we have made again the sweep of magnetic field, we have seen two regions correspond to the one mode and second mode. And you see, this is very similar to what was shown previously for the atomic Bose-condensed state. But here we can change the density, and as soon we have changed the amplitude of signal. For example, here with high excitation, we have seen overlap of these two states. And in this case, it was excited by exactly the same photons. But now, if we have do something with local magnetic field, or with switch, or by switch off the pumping, or change the frequency of pumping, we can again make some manipulation with this state, which is again qubit based on the two states. It's other one possibility to make quantum computing based on the Bose-condensed states. That's not all. There is very well known phenomenon of quantum computing based on the ring of superconductor, which is named, we can say, circular qubit or flux qubit. It happens because if you have the Josephson junction in the loop of superconductor, then you can possibility to have a counterwise and counterclockwise current, supercurrent of electrons. And due to the interaction of these two currents through the Josephson junction, we have always splitting of two states. One is counter plus convoke, and other minus state. They are splitted by the frequency, and this is basis of existing qubits of the quantum computer, which have announced just last year, basis on the superconductors. The same have been done also in the case of exciton-polariton states, which is now under discussable and theoretically described and experimentally near prepared. But in the case of magnon source of magnons, we can also make the ring and pump magnons from outside, just like I was shown on the slide when it was shown the superfluidity of magnons. We can pump magnons from here, keep density of magnons in this ring. Of course, as usual, as in the case of the conductors, we can make a p junction, for example, here. And then there should be splitting of counter-clockwise precession of spin current, spin supercurrent. And by splitting of these two states, we can also make somehow exactly the same phenomena like in existing superconducting qubits, but now at room temperature, in principle. Furthermore, we can make, for example, 3 p junction, and then we can make some kind of excitation and readout of states by additional strip lines, which are connected to the different part of this ring. These experiments are also under preparation. We have seen preliminary results, and of course, problem is relaxation. So we need a sample with much better, much longer relaxation time. Nevertheless, in principle, it should exist, this method. Third possibilities, we have also yttrium-filled garnet, but now we have two yttrium-filled garnet with the split between, jump between them. Then there is two possibilities. One is precession in phase of two magnons, and other out of phase precession. And of course, these two states correspond to two levels of minimum of energy, which was calculated by Bezryadina in our laboratory. And experimentally, we have seen splitting of the line. So we have seen, in the case of these two samples, with jump with the gap of 40 micrometers, we have seen that we have two series of signals which separated on 32 megacycles, which is more or less correspond to the theoretical prediction. And of course, there is two states with two coherent quantum frequencies, which can be used as a qubit again. So this next one possibilities. So finally, I want to say that we have very nice new system which has very many advantages. First of all, this is macroscopic coherent quantum state, which can be read out without of destroying the information. For example, like in this cartoon, you see we have cats in coherent quantum state, Bose-condensed cats, and then we want to know, is this cat died or alive? For this, we just need to see one cat to see that it's alive. So it means that all other Schrödinger cats is alive. So this state can be supported permanently, for example, by addition pumping of magnons. This state can be manipulated by RF power and RF frequency, or local magnetic field, or its gradient, or just by geometry of sample. Also, it can be manipulated by acoustic pumping, and even electric field through the Aronoff-Kasher effect. So you see, we have system extremely rich, which can be used for different by different method to used for create the starting conditions for calculations and then to read out the result. So, okay, so I guess I will stop in this point of view, and thank you very much for attention. And this subject is, you see, very, very in starting point comparing with the superconducting qubit, which have now history of about 20 years. Thank you very much.
Okay, thank you very much, Yury Mikhailovich, for your exciting and very fresh lecture concerning the magnon qubit, how to create those qubit by using magnon. Okay, is it any questions, dear guests? Okay, now in our session, there are 39 participants and
Vladimir Ivanovich has a question.
Yeah, please.
Not only me. My question is, I think that the interest to quantum computing is the increase in the velocity of calculations and to volume calculation, but you should manipulate by radio frequency power, but this manipulation is very slow in the scale of necessary requirements.
You see, this is very important point, is that for change the Bose-condensed state, you need to change not only one magnon, but you need to change 10 in 20 power magnons. It means the energy for change between states is not just frequency multiplied by H, but it's should multiply by n in 10 powers. So it means that the speed of, first of all, it means that the system is very stable against the temperature, because fluctuation of one photon doesn't change the state at all. You need to fluctuation of 10 in 20 power photons simultaneously. And this we can do only by external excitations. And as of course, the time for manipulation for the system can be very long for this time. So really now we have limited by the time scale of relaxation, and we have the quality of system is 10 in 5 power. So frequency of relaxation 10 in 5 power compares the frequency of resonance. So we have a 2 gigahertz now frequency of resonance. So we have time scale of relaxation about 100 microseconds.
By the way, this circumstance limits the applications, because this is only operative memory, yes, for
quantum
computations due to relaxation process. We cannot save states during long time.
Yes and no, because you see, if we have two states with Bose-condensed state, entanglement, so interaction between them, also multiply by a number of particles. So it means that interaction is very fast.
Yes,
and
but we should keep this information during a long time, but it's impossible in the case of that systems.
It's not true, because, for example, for this case, information is based on the phase relation between magnons here in ring, gradient of phase, and this gradient of phase live permanently, because we have permanently pumped the magnons, and these new magnons, according to the Feynman theory, replaced the magnon relaxation and keep the same state. This is very important, because if it's just independent oscillators, you have just put new oscillator and it's changed the state. But in the case of Bose-condensed state, the new particle keep exactly the same state as before. It's the same like a laser, when you have how it's named, вынужденное излучение. So new photons excited exactly the same state as photons stimulated. Yeah. So here's exactly the same phenomenon in principle, because this existing Bose-condensed state stimulate the creation of new magnons at exactly the same state.
Yes, and
so in this will be, in this case,
and the last point, it's impossible to create laptop, yes?
Well, why not?
Okay,
Yes,
thank you.
In principle, yes, we need just only some technological improvement.
Okay. Vladimir Ivanovich, thank you very much for your very interesting question, and also thank you very much for Yury Mikhailovich for the Very nice answers. But we should look for the watch, and I think all other questions we can make in chat. Okay. And now, so again, thank you very much, Yury Mikhailovich, for the very nice, wonderful, I guess, and exciting lecture. Thank you very much.